So at the top of your guided notes, next underneath Arrhenius and Bronsted-Lowry, you guys have a warm-up. I'll give you 2 minutes on this warm-up. This is actually one of our lowest objectives. So if you still don't know what atomic radius and size and ionization energy and electronegativity, make sure you make this as a priority moving forward so that we can talk about those objectives for the STAR exam. You guys have 2 minutes starting now to finish the warm-up. We'll quickly go through it. Okay, so that's time up. Let's go through each of these. So we want to rank the elements in order of increasing atomic radius or size. So remember the periodic table, as you move up a group and as you move across the periodic table towards fluorine, atomic radius decreases. Okay, so the order should actually be magnesium would be the smallest, then calcium, and then potassium. So as you move across the periodic table towards fluorine, as you go across, the size gets smaller, and as you go up a group, the size gets smaller as well. Okay. All right, which term refers to an ability of an atom to attract an electron in a chemical bond? It's either ionization energy or electronegativity. In this case, the definition is electronegativity. Ionization energy is the amount of energy it takes to break an electron off from an atom's orbit or an atom's orbital. So, what is the most electronegative element? Well, following the trend from the periodic table, you would think it'd be helium, because helium is the highest to the right, but it is not helium because the noble gases don't get electronegative values, so we move to the next closest one, and fluorine is the most electronegative element. This question sort of ties into the last one. Which group of elements is generally not assigned electronegativity values? That group is the noble gases, as I mentioned in the last group. We want to rank the following in order of decreasing ionization energy. So going from the highest ionization energy to the lowest ionization energy. In this case, electronegativity and ionization energy are related because if something has a high electronegativity, that means it also has the high ionization energy. Because if the atom is doing a really good job holding on to its electrons, it's really hard to break an electron off from the orbitals. So the order is actually exactly as it appears. It should be from fluorine to chlorine and then bromine. If you guys have any questions about that, I'd be happy to address it on Monday after school for my tutorial session, or if you just want to text me, we can talk about it as well. So So moving on, let's talk about Arrhenius and Bronsted-Lowry. So I want you guys to go ahead and fill in the definitions for each of these as I kind of talk through it. Arrhenius, his definition of acids was a proton producer in an aqueous solution. So you have a solution that is aqueous. We understand what that means. What we're talking about in a reaction is when it produces a proton and it is snagged by something else. So we talked a little bit about protons moving in autoionization the other day. The big thing I want you to note, if you notice at the bottom of the slide there, it says that, right down here, okay, it says that every hydrogen, so a hydrogen plus, equals a proton. And we're going to use that in the next part when we talk about identifying these acids. So let me talk a little bit about why there are two definitions before I move on. Arrhenius was an older scientist. He had some basic ideas about acids and bases, but Bronsted-Lowry is the more recent and the more accepted version of what our definition of acids and bases are. The main example or the main reason for that is because that if you look down here, NH3, ammonia, is now considered a base, when in the past it would have been considered an acid. So that is really pretty much the key distinction that you need to make here. If they ask you for an exception between Arrhenius and Bronsted-Lowry, or what is a good example of an Arrhenius acid but is actually a Bronsted-Lowry base, you should definitely make note that ammonia here is usually the example given. Okay, so looking at these definitions, you guys can read the definitions. I'm not going to sit here and do that for you. But what you need to do to kind of sum up, okay, acids are losers. So acids lose protons, so they're going to lose the hydrogens in the next part, and bases gain. So acids lose the hydrogens, and bases are going to gain. And we're going to use that definition to identify the Bronsted-Lowry acids and bases. Okay, so moving forward, I want you guys to fill in these notes as well. So we're going to fill in a little bit of background information on these guys. So what exactly should you focus on? Arrhenius has the more restrictive definition of acids and bases, so he leaves some out. The solutions have to be aqueous, and a base has to contain a hydroxide. And as I explained earlier, the main example of a base not containing a hydroxide is ammonia. Bronsted-Lowry's definitions is the more commonly used, the more commonly accepted definitions, and acids tend to lose hydrogens while bases tend to gain them. Okay, and remember those hydrogens in this case are referring to a proton. So under this definition, this part sort of sums up the exception I already talked about, that ammonia is considered a base under Bronsted-Lowry's definitions, but not considered by Arrhenius. Okay, so you're probably wondering, okay, that's great. How can I put this into practice? So let's take a look at how we're going to put this into practice. So if you could please flip your sheets over, and let's take a look. Okay, so let's take a look at our examples. So the first step in identifying an example, so here's our first example, is you have to identify the anions. Okay, so in my first solution here, this is hydrochloric acid. Okay, my anion in this situation, so my negative ion is going to be the chlorine. So I find the chlorine here, I'm going to locate it again on this side, and we're going to compare the beginning hydrochloric acid, so this one here, to the ending chlorine on this side. So if we look at chlorine, we can see that it has a hydrogen here. Okay, as we move across, as it undergoes the reaction, it actually loses a hydrogen. On this side it has a hydrogen, on this side it lost a hydrogen. So as I stated before, acids lose and bases gain. Okay, so we're going to identify hydrochloric acid as, not surprisingly, an acid. So the first couple examples are going to say, okay, that's obviously an acid, that's obviously a base, but as we move further on, it's going to be a little trickier to identify them. So let's take a look at the second compound in here. We have potassium hydroxide, and let's just take a look at this hydroxide. So this is our anion in this case. So the hydroxide on this side, if you rewrite water as HOH, right, in this case the OH does not have a hydrogen. On this side it's gaining a hydrogen, so it only has one on this side, one hydrogen here, and then it has two on this side. Okay, so it's the one gaining a hydrogen or gaining that proton, so that is what makes it a base. All right, so let's try another example in case you're kind of lost. Okay, remember the first step. So let's try the second step. Or sorry, let's try the second example, the first step. You start by identifying the anion. So this is calcium hydroxide here. Okay, so we have hydroxide as our anion. That's the negative. Let's find hydroxide on this side. It's here in the water. Okay, so if you rewrite H2O as HOH, you can see that hydroxide much easier. Okay, so here we have hydroxide. Okay, it didn't have an H in front of it here. Over here it is gaining an H. So remember the rule, acids lose, bases gain. So in this case it's going to gain an H, which makes it a base. Okay. On this side, our anion is PO4. Okay, so phosphate. So this is phosphoric acid. We take the phosphate and we look here. It has 3 H's here. Here it lost all 3 of them, so it's the one losing a proton. It's losing those H's. Okay, so that's what makes it a acid. Okay. Acids lose, bases gain. Okay. So let's try this third example. It's a little more unconventional. So if you look at these two, the first two examples, you can see hydrochloric acid, we know that's an acid, it's in the name. Phosphoric acid, we know that's an acid, it's in the name. Okay. But with this example, we're not really sure what is the acid and the base. So we really have to track what is happening to that hydrogen, what is happening to that proton. Okay. So here we have fluorine. It's clearly the anion because it's negative and it's by itself. Okay. So we look at it on this side, and then as we move across, we can see the fluorine on this side. It has gained an H. So if it's gaining that proton, it's gaining that H, that would make it the base because acids lose, bases gain. Okay. So by default, we can sort of consider this one an acid, but let's just sort of check now. Okay, so this is the hydroxide. You can see it here, OH. Okay, so this is really HOH if you rewrite it in a different formula. So here the OH has an H in front of it. Okay, so this is really HOH. And then that H is going to drop off and go to the fluorine, so it only has an OH. So the OH started here with an H, it lost one, so it is the acid. Okay, so in this case, water is actually acting as an acid. Which is kind of hard to think about because we know that water doesn't have an acidic pH. Okay, I want you to try the next two with a partner, and then we'll come back in my next video and we'll talk about exactly which one is the acid and which one is the base. Okay, so try these next two with a partner. Give you guys about, I don't know, about 3-4 minutes to try them with a partner. Remember to track the protons. Acids lose, bases gain. Okay, see you in a second.